Inside every single one of your devices, there's this invisible universe. Trillions of electrons are just zipping around, carrying all our information. For the last, 70 years, we've built our entire digital world on just one of their properties, their charge. But what if I told you they have a secret, a hidden property that we've pretty much ignored, one that could kickstart the next information age? Well, today, we're pulling back that curtain. We're talking about spintronics.
Okay, so here's our game plan. First, we'll look at this hidden wall our current electronics are smashing into. Then, we're going to uncover the electron's secret spin and see how that creates magnetism. From there, we'll dive into the dawn of spintronics, see how it's creating memory that never forgets, and finally, we'll ask the big question. What could this next information age built on spin actually look like?
All right, first things first. To really get why spintronics is such a game changer, we have to understand the huge problem it's trying to solve. And honestly, it's a problem you deal with every single day.
Have you ever really thought about this? I mean, your computer's main memory, its RAM, it's blazingly fast, right? It lets you jump between a dozen apps without a hiccup. But the second you pull the plug, poof, it's all gone. Every tab, every unsaved document. Why is our fastest memory so incredibly forgetful? Well, that brings us to this really crucial split in how our devices work. On one hand, you've got volatile memory, like RAM. It needs a constant stream of power just to remember what it's doing. And on the other hand, there's non-volatile memory, like your SSD. It holds onto your files forever, using magnetic tricks that don't just vanish when you turn it off. For decades, we've had to make this trade-off. You can have speed, or you can have permanence. You couldn't have both. And the real issue here is that our whole digital world is built on just one thing, moving electron charges around. But pushing charge creates heat. It burns a ton of power, and as we just saw with RAM, it can be super temporary. So as we try to make our gadgets smaller and faster, we're just hitting a fundamental physical wall. We need a new way of doing things. So where do we find this new approach? Well, it turns out the solution has been hiding in plain sight this whole time. It's a fundamental property of the electron that we're only now really learning how to use. And this isn't some shocking new discovery either. I mean, check out this quote from the journal Science. We've known about electron spin for ages. We just kind of built our entire technological world without it. Spintronics is all about finally using this other incredibly powerful property. So what is spin? Okay, forget all the complex quantum physics for just a second. The absolute best way to picture it is to think of every single electron as having its own tiny built-in compass needle. It's a basic property, just like its charge. And here's the kicker. That little needle can only point in one of two directions. We call them spin up or spin down. That's it. It's a perfect binary system, a 1 or a 0, built right into the fabric of the universe. So we've got trillions and trillions of these tiny compass needles inside every material around us. What do you think happens when they stop pointing all over the place and actually start to line up? You get magnetism. That's all magnetism really is. It's just a massive team effort with countless electron spins all agreeing to point in the same direction. The force that holds a magnet to your fridge, that's a direct, real-world consequence of this tiny quantum property. And the best part? It's stable, it's strong, and it doesn't need any electricity to just stay that way.
Okay, now this is where it gets really, really clever. Scientists and engineers figured out how to control and, more importantly, read the direction of these little compasses at a ridiculously small scale. They figured out how to turn magnetism into digital information.
And that brings us to the formal definition. Spintronics is this whole new kind of technology where information isn't just about whether an electron is there or not, its charge, but which way its internal compass is pointing. We're using its spin. And the hero of this whole story is a tiny little device called a magnetic tunnel junction, or an MTJ. The easiest way to think of it is as a microscopic light switch. It's basically a sandwich made of two magnetic layers with a crazy thin insulating layer squished in the middle. Okay, so let's see how this switch actually works. In one of the magnetic layers, all the spins are locked in place. But in the other layer, we can flip them around. So what happens when the spins in both layers are aligned, all pointing in the same direction? In other words, when they're parallel? Well, electrons with that same spin can just zoom right through the barrier. It's like a VIP lane opens up, creating a state of really low electrical resistance. We can measure that super easily, and we can call that state a digital 1. But here's the really brilliant part. What happens if we use a tiny magnetic nudge to flip the spins in that second layer? So now they're pointing the exact opposite way. Now they're anti-parallel. And boom, the magic of the MTJ. Now, it's incredibly difficult for electrons to get through. The VIP lane is closed, creating a state of high electrical resistance. And that's our digital zero. It's a stable two-state switch based purely on which way the little compasses are pointing.
So the crucial takeaway here is that this simple, elegant little switch directly solves that huge forgetful memory problem that we started with.
Take a look at this graph. This shows you the resistance of one of these memory cells as it gets switched. That absolutely massive, sharp jump between the low resistance on state and the high resistance off state, that is everything. That's a clear, reliable, instant bit flip. That's the foundation for a whole new kind of memory.
And this new memory is called MRAM, which stands for magnetoresistive RAM. Let's just put them head to head. Your old school DRAM, your RAM, stores data as tiny electrical charges that are constantly leaking away. That's why they need power all the time. But MRAM, it stores data in the stable direction of electron spin. Once you set a bit to a 0 or a 1, it just stays that way. Power on, power off, it doesn't matter. It never forgets.
And the benefits here are just mind-blowing. You get the non-volatility of an SSD, it never forgets, but with the blazing speed of RAM. It doesn't wear out like flash memory, so its endurance is incredible, and because you're not constantly pumping electricity into it to keep it alive, the power consumption is ridiculously low. This has all the makings of a universal memory, one type of memory that could do everything. But look, universal memory, that's just the beginning. The ability to control electron spin opens up a completely new toolbox for building computers. So let's just peek over the horizon for a second.
And what's on that horizon is really exciting. Researchers are already developing something called SpinFETs. These are new kinds of transistors that could lead to processors that are way faster and use way less power. They're also working on things like domain wall memory, which could let us store even more data in smaller spaces. And maybe the wildest part? In the world of quantum computing, that simple up or down state of an electron spin, well, that's a perfect candidate for making the qubits that are going to power the computers of the future. So let's end with this one thought. For the better part of a century, we have built a civilization-changing revolution on just half of what the electron can do, on its charge. We are only now finally unlocking the other half, its spin. So imagine computers that turn on instantly, no boot up time, because they never lost their memory. Imagine phones that last for weeks on a single charge. It just makes you wonder, if charge gave us the information age, what kind of world are we going to build with spin?